Okay, welcome back, and we're going to move on with our next presentation. Next, we have Roie Schwaber Cohen, who is from Pinecone. He's a staff developer advocate and a full-stack software engineer with a deep passion, everyone's passionate these days, for AI and data-intensive applications. And he's going to be talking today about better semantic search with hybrid sparse-dense search. So, without further ado, I'll hand over to you, Roie.
All right, everybody. So my name is Roie. Thank you for the introduction. And I'm a developer advocate at Pinecone. For those of you who don't know, Pinecone is a vector database. Our goal is to make it easy for developers to build high-performance vector search applications. Don't worry, this isn't a pitch. Instead, I'm just going to talk about sort of our approach for improving semantic search with hybrid vector search, a term that all of you have heard, I've heard spoken about many times today and yesterday. The industry has really been on a long journey, coming up way to produce better search results, but also to come up with ways of understanding user queries better. And in that journey, there have, of course, been two main approaches for representing semantic information that is relevant to the session, those are sparse embeddings and dense embeddings. And both of them obviously have pros and cons. And what we'll do today is explore both of them a little bit and kind of talk about how we can kind of overcome their weaknesses and kind of benefit from their strengths. So quickly, the agenda for the talk. We'll start with a short definition of what embeddings are for anyone not yet familiar. We'll take a look at the historical progression of semantic embeddings that will hopefully orient us a little bit. We'll dive into a couple of sparse embedding methods that most of you probably already know, and then explain what dense embeddings are. We'll talk about how dense semantic search applications work. And then finally, we'll dive into hybrid vector search, and hopefully with the help of the demo gods, we'll do a short demo. So let's start with some definitions. What are embeddings? So embeddings are basically just numerical representations of semantic information. They basically capture essential features and relationships of discrete objects. And those objects can be anything from words to sentences to documents to images and so on. And obviously those representations are in the form of vectors, so just lists of numbers. In other words, embeddings basically allow us to apply all sorts of mathematical utilities to things that have meaning. And when we do that, we can gain new insight and do interesting things. The most relevant of which for this talk is semantic search, but it's definitely not the only thing that one can do with embeddings. So we'll keep it very abstract at this point, but as we move on, we'll get a bit more concrete about how we use embeddings. So I'll start by setting the scene a little bit and discuss how semantic embeddings evolved. I just wanted to just lay out some important historical markers to give us some context for the rest of the talk. So before I start, I just want to say this timeline is by no means exhaustive. I'm going to just call out some algorithms and tools that I think were very substantial in moving the entire field forward, but obviously there's been a lot more work in the field than is mentioned here, so no offense to anyone. One of the earlier techniques for representing text in continuous vector space was VSM, the vector space model. And that was an approach that applied, that was sort of the first approach that applied the geometric properties of bag-of-word vectors and sort of enabled similarity measurements using geometric operations, like distance, cosine similarity, etc. It was developed in the 60s, which is kind of astonishing to think about. All of this is not new. Later on, we've seen TF-IDF that came from Peter Loon and Hans-Peter Loon in the 50s, and Karen Spark-Jones in the early 70s, and we'll talk about TF-IDF a little bit later. After that, we got BM25, which is a sort of an extension and an improvement upon TF-IDF. Then we started shifting towards techniques that relied more on neural network. The first to be very, very popular was Word2Vec, that came out in a paper published in 2013. It was really the first widely used algorithm that leveraged a neural network model to learn word associations from a corpus of text. Of course, there were other attempts, but Word2Vec was really the first one that took off and became enormously successful and sort of paved the way to other algorithms like GloVe, FastText, and others. Then in 2016, the famous paper Attention is All You Need came out, and we got BERT, which was the first really incredibly popular transformer. Jump to 2021, we have GPT-3. Back then, it was the largest neural network ever produced, only to be outshone by GPT-4, that is even bigger than GPT-3, but more importantly is also multimodal, which means that it is capable of embedding both text and images, and not just text. And that's important because it really informs the internal embeddings in a much deeper level, and we'll see how that kind of comes into effect a little later on. So this was a really blazing fast and really reductive overview of the last 60 years in semantic embeddings. As you can tell, nothing really much has happened. This field is really boring. I don't know what we're all doing here. We can really tell that sparse embeddings were pretty much the cornerstone of semantic search, but let's get a better intuition about how they work, what are they good for, and what they're maybe lacking. So, simply put, sparse representations, and this was already discussed ad nauseum by a lot of other speakers, are sparse because they hold values in a vector that are dispersed sparsely, and so we have many zero values and very few numbered values within the vector. But why is that? Let's get a better intuition on why these vectors are the way that they are. So let's consider this very classic example of sparse embedding. That's what we know as the bag of words model. So you see the sentence on the left, the quick brown fox jumped over the lazy dog. Basically, we have a vector that represents the occurrence of every unique term within that sentence. So the word the appears twice, and all the other words appear once, right? So when we start with just that sentence, we have this vector. There are no zero values yet. But when we add another sentence to this corpus, our vector sort of changes, because now we've increased our vector to include the entire vocabulary. And since the second sentence, the green frog jumps over the log, doesn't include many of the words in the vocabulary, we are now seeing more zero values in that vector. Okay. So now we have a better sort of intuition as to like what makes sparse vectors sparse. Let's talk about the two most well-known sparse embeddings out there. The first one is TF-IDF, as I mentioned. It basically looks at the term frequency of in a document and calculates the inverse term frequency in the entire corpus. So if a word shows up a lot in a document, but is rare elsewhere, then it's probably really important to that specific document. But on the other hand, if we have a word appearing in all of our corpus, in high frequency, that sort of lowers the importance of that term across the entire corpus. Then we have BM25, which basically expands upon TF-IDF and adds frequency saturation and document length to sort of normalize cases where the documents are very, very long, so that we don't get a case where a term that appears in a document that's very, very long sort of takes over the entire corpus. So these two techniques have been widely used to produce sparse embeddings and are still used these days in many, many applications. So next, let's talk about sort of the pros and cons. So sparse embeddings are generally more performant than dense embeddings, and they generally cost less to use. We'll talk about why that is a little later. They're very well suited for exact matches, and if we know what we're really looking for, they work really great. So if our query terms are exactly what exists in our indexed corpus, they're going to be very performant. And for that exact reason, they work really well for domain-specific terminology, right? So it doesn't rely on a big generalized data set for the embeddings, but rather because it's specific to the corpus, it will be able to handle even the most rare keywords. On the other hand, sparse representations tend to be highly dimensional. So as we saw before, when I add more sentences to a corpus, and the more content I add to a corpus, my vocabulary grows, and so the dimensionality of my vectors grows as well. And that means that I'm now hitting the curse of dimensionality, which means the higher the dimensionality, the lower the performance, the bigger the memory consumption, and the computational complexity grows as well. Perhaps the biggest problem with sparse embeddings, and that's really the main challenge with all keyword-based search, is that it doesn't really reflect the meaning behind the queries. So I either have the term indexed or I don't have the term indexed, and if I don't have the term indexed, I'm sort of out of luck. So when the user comes to express themselves and write their query, they're sort of forced to work against the limits of whatever it is that I indexed, and they sort of have to guess how to interact with my indexed corpus. They can't just ask the question the way that they would naturally would, and form the query the way that they naturally would, and that's a very limiting factor in a lot of different keyword searches. We all know about the very unnatural ways that we have to, for example, interact with Google and come up with the Googleese that would actually work. So to explore new ways of getting a little bit more meaningful search results and allow users to just say what they mean instead of what the search engine wants them to say, let's take a look at dense embeddings and semantic search. So, as the name suggests, dense embeddings are the absolute inverse of sparse embeddings. Instead of having many zero values, dense embeddings typically don't have any zero values in them, like it was stated before today. And the reason for that is because they're created a completely different way from the way that sparse embeddings are created. To create dense embeddings, we use embedding models. Those could be models like Word2Vec, Glove, BERT, SBERT, GPT, all of the sentence transformers that are available on Hugging Face and more. And these models are trained by being exposed on to immense amounts of textual data and other types of data. And they basically learn how to predict or even understand language to a certain extent. There are several techniques for training these models and then fine-tuning them, but that's kind of out of scope for this talk. So instead, let's see what type of outputs we're going to get from these type of embedding models. So dense embeddings basically capture the relationship between embedded objects, like, again, words, sentences, images, audio, etc. And more importantly, they are able to capture, in that sense, the meaning of those embedded concepts. So once they are trained, the model basically has a representation of these concepts in high-dimensional space, and we can measure the similarity between them using several similarity measures, like, again, cosine, dot product, Euclidean, and so on and so forth. So as you can see in the example that I have here, I have a bunch of terms like the days of the week, and in the embedding model, we're expecting to see these terms in close proximity, geometrical proximity to one another. This is, of course, a reduced form of the actual dimensionality of these models, but this is just to give us a better intuition of what things look inside the embedding model. So dense embeddings would basically work the same way on things with bigger context. So different models are used for different purposes. So for example, SBERT and GPT are trained to encapsulate contextualized embeddings, meaning that they are aware of like the context of the entire sentence, for example, in this case. And so we can see up in the left, a little boy is walking, and close to it, a sad boy is walking. So there's like a closeness between those two sentences because there's walking involved, there's a boy involved. They're not the same because one is little and one is sad. And then on the right, we see, look at my little cat, completely different sentence, completely different contextualized, a completely different context. And so the model is capable of saying, well, this sentence is completely unrelated. This basically gives us a better and more granular understanding of each word, of each of the words in the sentence, the paragraph, the document that we're working on. And it helps us, again, produce more meaningful results when our users are feeding our system with not just words, but also sentences, documents, and more. So let's talk about what dense embeddings are good at and what they're bad at. So as I mentioned before, they're excellent at capturing relationships between concepts and their meaning. They allow us to better understand context and semantics a lot better than sparse embeddings are. They outperform sparse embeddings in tasks like document similarity and sentiment analysis. And more importantly and more holistically, dense models, dense embeddings basically represent language more naturally than sparse embeddings, and they allow us to build applications that leverage that capability to produce more natural user interfaces. So again, instead of having to speak Googleese, I can ask a question in natural language and rely on my embedding model to produce results that would reflect my actual intent without having to hit any particular keyword in an exact match. They're more compact than sparse representations, so technically speaking, they are they benefit from the fact that they're of lower dimensionality, suffering from less pain with a cursive dimensionality, so they're more computationally efficient. And lastly, they can be fine-tuned for specific tasks and domains that allows them to perform better in those domain-specific scenarios. But that comes at a cost, so fine-tuning is not a free thing. It could be very time-consuming. It will require very specific domain knowledge that many don't have. So that's not necessarily a sort of a path that many are going to want to go on. Beyond that, they don't really generalize well to phrases or terms that were not present at the time where they were trained. And that means that if you, again, take them to anything that is domain-specific, that the model has never seen before, it's going to have a hard time actually creating embeddings that are meaningful. And so, unlike sparse representations, again, dense embeddings don't support exact matching, and that, again, makes it harder to find exact keywords that you're actually looking for. So you're missing out on all of the goodness. If it is intended that you want to use an exact match, you're going to miss out on that because the embedding model doesn't really care, and it's going to find the closest thing that resembles the term that you fed it. Okay. So we've seen how dense embeddings work, pros and cons. Let's take a quick look at how semantic search works when it uses these dense embeddings. So here's an architecture for a typical application that uses dense embeddings and a vector database or an index. We usually start with a content encoding phase. So we're taking our content, our documents, our corpus, and we create embeddings for that entire corpus. We then basically take those embeddings and store them in our vector database or our vector index. And then the application, when it's time to actually query, creates the embedding and then queries the database with using the same embeddings produced by that same vector and gets the results back. Usually there's a stage which requires that we match some external data that wasn't necessarily stored alongside with the vector, although depending on your database, you can store documents that are not just the vectors in the vector database as well. So now we have a good understanding of both sparse and dense embeddings. Let's talk about hybrid vector search, which is what we're here to talk about. The question is really how can we tackle using both sparse embeddings and dense embeddings and to basically improve the search experience and kind of get the best of both worlds. So there are several approaches to this. I'm going to talk about two main approaches. One that was sort of already mentioned yesterday, which is sort of a two-stage retrieval strategy, where we initially start with results that come from our sparse embeddings. We then re-rank those results using the dense embeddings, and then we finally produce the final set of results. This approach works well because we're using a very fast and performant sparse retrieval method that definitely takes less time than doing just dense embeddings. And then we're using a slower re-ranker on the subset of results, which takes obviously less time. We can also use other types of re-ranking alongside our dense re-ranker. We're not just limited to using dense embedding re-ranking. So that's another potential benefit of using this approach. On the other hand, this is basically dependent on us trusting that we're going to get a good result from our initial sparse embedding and because whatever comes after is dependent on that initial superset. And so depending on your scenario, this might be sufficient, but there are, again, other methods that you could use. So, and again, let's ask ourselves, like, what if we don't really want to limit ourselves to that initial subset selection, but we really want to have these sparse and dense embeddings combined into a single query that produces the final result. So this is how we would go about doing sort of the same thing in a more parallelized fashion. So again, there are, like I mentioned before, in any dense process, in any indexing process, we have our indexing and storage phase, and then the query phase. So in our indexing, we basically create dense representations and sparse representations for every document in our corpus, whatever the unit is. And we create a hybrid vector that includes both dense representations and sparse representations. So we would use BM25 for the sparse representations, and then BERT or SBERT or GPT-3 or Ada, whatever it is that we want to use for the dense model. And then finally, we'd store those hybrid vectors in our index. And then on query time, when the user submits a query, we again create a dense representation for that query, a sparse representation for that query. We combine them and create a weighting between those two representations so that, and I explain it a little bit further down in the demo, like what advantages that has. Basically, it allows us to decide which of these components we want to leverage more at query time, right? So we're not limited to only using our sparse or only using our dense. We can define, like, we want to use our dense more, or we want to use our sparse more. And then we get a weighted hybrid vector. We send that query to the index and get back our top K documents. So again, like, this has the added value of not having to decide right up front which of these methods we want to use. And that has a great advantage for a lot of different scenarios, again, because we're not locked into any one of these in particular.
Sorry, clarify the right two blocks.
Yes. So we have our we'll start again from the query. We create the dense and sparse model representations. We then create a hybrid weighting, meaning there's going to be some factor that is associated with the dense, some weight associated with the dense representation, some factor associated with the sparse representation, and then finally we're going to have a vector representation that represents that weighting sort of combined. Does that make sense?
No. So you're averaging these vectors from the two. What exactly is going on in the weighted hybrid vector?
So there's a weight factor that is being basically, I'm taking the actual vector and I'm creating a multiplication of that value, and then basically combining it in my weighted representation. So my hybrid vector representation still has a sparse value and a dense value, but now they have some factor associated with them, which basically changes the index itself is in a dot product space, and it changes the size of the dot product space, and that basically tells the index how to what weight, right, it needs to give, and what kind of influence is the sparse representation going to have, and what influence the dense representation is going to have. Maybe in the demo this will become a little clearer because I'm doing exactly that. Okay. So just to sum up, sparse and dense vector search basically combines the strengths of both sparse and dense representations. It offers the semantic richness of dense embeddings and the exact keyword matching capabilities of sparse embeddings. And then hopefully that produces, again, better, more accurate search results that are not susceptible to the pitfalls of either one of these methods when they stand alone. It is sort of non-committal in the sense that you are not required to decide which of these methods you're going to use before you issue the query. And then because it involves this, because the sparse representations are involved, it's easier to then go into domain-specific fields where dense embeddings usually don't perform as well, without having to do a lot of fine-tuning, yeah, you can basically avoid all that work. On the con side, hybrid search definitely can be slower than either sparse or dense search on their own. You're basically, because you're working with both of these embeddings, you're essentially querying two separate indices, one that is a sparse index and one that is a dense index, and you're basically doing double the work. It does require more work before you even index, so you have to create the representations for the dense, you have to create the representation for the sparse, and index them both. So to sum that up, yeah, like there's a lot of benefits and flexibility in this domain adaptation, but it can be slower. So we have to really carefully consider the trade-offs of whether or not we want to apply hybrid search or not. In a lot of cases, it does produce results that are significantly better that could not have been produced with either one of these methods on their own. There's some performance metrics that I can share with you. So generally speaking, we have a comparison between a single vector and a hybrid vector. You can see that in a lot of cases, using hybrid vector with SPLADE or BM25 outperforms the relevancy scores, again, for this NDCG 1000 metric, but not always. And in general, we find that SPLADE, which is a more recent embedding, sparse embedding technique that sort of is capable of learning from a dense embedding model to sort of improve its own sparse embeddings. It sort of outperforms BM25. So that's that. And with that, I'm going to jump to a quick demo, and hopefully the weighting situation is going to be better explained. Okay. So I hope that you can all see this. It's a lot of tiny words. We're not going to go through the whole thing because it's a lot of data loading and whatnot. Suffice it to say that I have a Quora data set that's been preloaded into an index. It basically includes a whole bunch of different questions that come from Quora. And what we do here is create the index and then upsert all of these sparse and dense embeddings that were pre-calculated for us, so we don't have to go through this whole embedding process right here. We're going to pick a question from this data set. So how reliable is a Mitsubishi Eclipse? So as you can tell, like there are two words here that are pretty domain specific. So Eclipse could mean a whole bunch of different things. Like the semantic interpretation probably wouldn't have anything to do with Mitsubishi, and we would expect the dense representation to actually perform kind of like meh. And so now we want to basically see what happens when we use different weightings between the sparse representation and the dense representation. So just to clarify, again, what happens in this weighting situation. So we literally take the vector itself, right here, where we have the sparse vector values, right? And we have the vector here is the dense vector values, and we create we literally multiply it by the weight factor that we're looking for. So the alpha is going to be, if the alpha is, for example, 0.5, then let's say it's 0.2, then the alpha here is going to be 0.8, and that basically changes the actual values of the vector itself. And since, again, we are within a dot product space in an index, what happens under the scene is basically that the vectors become bigger or smaller. Their angular direction does not change, so their meaning, in so to speak, does not get changed, but the amount of influence they have on the final result does change. I hope that clarifies it a little bit better. And if not, we can tap into that a little later. So let's run this with only sparse. So as you can see here, I'm giving it an alpha of 0, and I get back the results. Well, I get back the question that itself, and then I get what is the best type. Let's see, just like open this up. What is the best type of brand of oil to use for the Mitsubishi Eclipse? Another question about Mitsubishi, etc. Let's roll down to see what happens with only dense. So I get Mitsubishi Eclipse reliable, again, the question itself, and then the Eclipse Neon is a good IDE, which is not really what we wanted, right? And so when I go back and I go to an alpha of 0.6, and I try that again, my result set is now, again, not exactly completely better, but I'm seeing more results that have something to do with Mitsubishi and less results that have nothing to do with Mitsubishi. And that's exactly the reason why we want to use these sparse embeddings in conjunction with the dense embeddings to kind of cover for the shortcomings of those dense embeddings. And that's all I have for you. Questions?
Okay, thank you very much. And we're now going to have some questions, and I believe we might have some online as well. So, do we have a question? First hand went up was, well, I'm going to come here because you've got a question for Trey. Doug and Max are trying to balance. So, Tito, let's come to you.
Thanks for the clear presentation. In a hybrid model, I'm wondering whether there's any intuitions at this point regarding whether certain types of queries benefit more from a higher weighting on vector-based or dense embeddings versus sparse embeddings. So what I mean by different types of queries here, it could be referring to known item searches versus exploratory, broad, narrow. Do we have intuitions at this point?
So again, this is really anecdotal. So I mean, and it's sort of very subjective at this point, I think. But I would say that whenever anything domain specific is involved, right? Like anything that's known and it's basically unlikely that a generalized model would have encountered a term enough times, right, to make it into something significant. Those are cases where sparse would probably work better. So in general, when we see customers that are indexing very domain-specific corpuses, we definitely see a value in tilting things towards sparse. And when, again, the user doesn't know what they're looking for and they're trying to get an intuition and more an exploratory kind of thing, things tend to go towards dense, again, because it helps with disambiguation a lot. With that said, it's exactly the blend of the two. that really helps, because you can really start from really broad things, but then potentially things that would be associated with both that wouldn't come on if you used either of them on its own, sort of fall in the Venn diagram of what you get back, right? So like you saw here with this Mitsubishi thing, there was a known term like Mitsubishi Eclipse, right? And then other terms sort of crept up, like other cars, for example, right? And it's possible that the dense embedder would actually be very fixed on Mitsubishi because it may have known it, right? And because it might have been, right, that it had been associated with other terms like other cars that the sparse embedder would know, right? And so, like, I think that in a lot of cases, like when you don't know what to do, producing sort of an equal blend is also helpful.
Thank you. Okay, so we have a question from our online audience. Chris Burrito asks, for dense embeddings, let's say my corpus of documents is a bunch of 10 or 20 page PDFs. Does each PDF become its own embedding, or do you embed in a much more granular level, word, phrase, sentence, paragraph? How do you determine similarity between a 3 or 4 term input query and a 20 page document?
Yeah, that's a great question. So the answer is that you don't, right? So like if you expect your queries to be very, very short, then you probably want to not embed entire documents, although there's a good chance that, again, with embedders with embedding models that have been trained on highly contextualized data like BERT, like SBERT, like GPT, they do deal with these situations pretty well. So basically what we recommend doing is chunking the information first. There's a lot of there are a lot of different techniques for chunking and reasons for having a certain size chunk, or how do you exactly cut between these different chunks, and whether or not you should have an overlap. But the main point is that there is no one size fits all, right? It really depends on the type of content and the type of query that you're going to have. In that particular case, if the queries are pretty short, I'd recommend not embedding whole documents, but rather creating smaller paragraph level embeddings, and that would probably be well performed.
Fantastic, thank you. Okay, so let's come over here. Any other questions from the floor? Okay. Peter, you're right at the back. I'm going to come up to you, I think.
Thanks. Yeah, this is great. I think the sort of linear combination of the two scores is like a great starting point for people that are starting to work with this. Do you see that this is enough, right? And like we're picking a magic number. It's going to work in some cases. It's not going to work in other cases. Are you looking at different sorts of fusion methods that are out there for different ways to sort of cross the streams more effectively in the future? Or like, what's your general perspective on this?
Yeah, honestly, this is pretty new to us, and to me personally. So I can't talk to like any particular future ideas of how to do this. What I am, again, experiencing myself is that guessing is not great. And there's definitely room for improvement in terms of how you find heuristics for actually figuring out the best weighting between sparse and dense. I think that like it's right now the best I can say is that it just really depends on the scenario that you're looking at, and on trial and error, like many things. Yeah, I don't have a much better answer to that, unfortunately.
Okay, so we've got a related question perhaps from online. We have Anu asks, Dave DeBar asks, can the weighting for the dense and hybrid scores be learned with machine learning, and do the best weights vary across query classes?
Sure. I mean, that sounds like a really interesting idea. I mean, I'm guessing that if you have enough samples that and labeled data, that would tell you whether or not that weighting produced desired results. That's something that could be learned over time, and sounds like a very interesting idea.
Okay. And I'm going to finish with one more question from our online audience, because they do sometimes get the second choice. We've got Anno again asks, is it important to domain adapt and fine-tune a dense passage retriever to get good performance on a domain-specific application?
Sorry. Can you repeat that?
Is it important to domain adapt and fine-tune a dense passage retriever to get good performance on a domain-specific application, e.g. legal or financial?
Yeah, I mean, again, so whenever domain-specific scenarios are involved, it really, again, it depends on the models that you use. There are a lot of models out there that have already been fine-tuned on legal material. If you're dealing with something esoteric, then and you're using a general language model, a foundation language model, you can definitely expect for it to not perform well as far as your legal terms go. So in those cases, yes, absolutely, it's crucial.
Fantastic. Well, I'm afraid we're going to have to leave it there, but if you do have further questions, do come down. I'm sure our presenter will be hanging around for a few minutes or catch him during the day.
Yeah.
So thank you very much.
Thank you.